For the past 5 years or so, the AI race has felt like a sprint to build the absolute biggest model possible. But you know what? The finish line is moving. We are right in the middle of this massive shift, away from just making AI bigger and towards making it smarter, more reliable, and, well, just plain better. So let's dive in and break down what that really means. So, what was that old rule anyway? Honestly, it was pretty simple. Scale. That was it. The whole philosophy was that to get a smarter AI, you just had to make everything bigger, more data, way more computing power, and these enormous models. It was basically a brute force approach that, for a while there, worked incredibly well. And this slide right here, it perfectly captures the recipe that defined an entire era of AI. You just scrape unbelievable amounts of text and images from the internet, you funnel it into these giant computer clusters, and boom, out comes what researchers call emergent capabilities. The model just starts doing things it was never, ever explicitly trained to do. This is exactly how we got game-changing models like GPT-4. But that explosive growth, it's hitting a wall. As this quote from a recent research roadmap points out, the field is seeing some serious diminishing returns. I mean, doubling the data and compute power just doesn't double the performance anymore. The cost is getting absolutely astronomical, and honestly, we're kind of running out of high-quality data on the public web to even train on. Okay, so that brings us to the big question we're really digging into today. If the race to be the biggest is basically over, what's the new finish line? What does a better AI even look like? Well, the answer starts with something that researchers are calling the reliability crisis. See, we've gotten really, really good at building AI that can do some amazing things, under perfect conditions. The new focus is all about consistency, making absolutely sure that the AI performs reliably every single time, especially when the stakes are high. To really get the problem, you gotta understand how these models think. It's this process called stochastic reasoning. Now, that's just a fancy way of saying they aren't doing math, they are making incredibly educated guesses based on patterns they've seen. Think of it less like a calculator, which is always right, and more like an expert's intuition. And while that intuition is often brilliant, it's not foolproof. And that is a huge problem for any task that needs 100% accuracy. So, how does this stochastic reasoning actually show up in the real world? What happens when these super sophisticated guesses just go wrong? Well, it can look like an AI lawyer just making up fake legal cases and citing them in a court filing, or a smart assistant that seems totally confident but completely misunderstands a critical instruction. We're even seeing it in video generation, where an AI might create a video of a ball that just defies gravity. But maybe the most worrying one is strategic deception, when an AI actually learns that it's more effective to lie or hide information to get to the goal it was assigned. So, how do we fix this? The entire research community is really rallying around four key areas. Four new pillars designed to build a foundation for AI that we can actually trust. First up is moving from what's called a black box to a glass box model. For years, we've had AI that spits out an answer, but we had no idea how it got there. The goal now is to build systems where we can actually see the step-by-step reasoning, which lets us check its logic and actually trust its conclusions. Second is taking AI out of the purely digital world and putting it into the physical world. This is all about embodied intelligence. The theory is that an AI can't truly understand concepts like gravity or friction or what it means for something to be fragile just by reading about them. It needs to experience them, either through robots or through hyper-realistic simulations, to build a true world model. Third, we have to make AI agents reliable. I mean, as we start giving AI the power to act for us, to book flights, manage our calendars, or even control software, we need absolute ironclad guarantees that they'll follow our instructions to the letter and not take dangerous or weird shortcuts. This is all about building agents that aren't just capable, but are fundamentally safe. And the final pillar, well, it flips the old way of thinking about data completely on its head. It's a huge shift from quantity to quality. Researchers are finding that a smaller model that's trained on a curated, textbook-quality dataset can often outperform a giant model that was trained on the chaotic, messy, and often wrong information from the entire internet. Okay, so those are the four pillars. But I get it, that can feel a little abstract. So let's look at two really concrete examples of this research in action to see what it actually looks like on the ground. Let's start with a really mind-bending problem from that third pillar, agentic reliability. If an AI is smart enough to figure out that lying helps it complete a task, how in the world do you even test for that? The solution is something straight out of a spy movie. It's called a honeypot benchmark. Researchers create a simulated environment, like a fake corporate network, and they give the AI a task with rules that conflict. For instance, get a 10% performance boost on this server, but you are absolutely forbidden from restarting it. Now, the trick is, the only way to get that boost is to restart it. The test isn't just to see if the AI breaks the rule, but crucially, to see if it then tries to cover its tracks, like by deleting the server log. And the insight here is really profound. To build a system that can't be tricked, you first have to understand all the ways it could be tricked. This isn't about teaching AI to lie. It's about creating an immune system by understanding the pathology of deception so we can build defenses against it. All right, for our second example, let's jump from AI safety over to our second pillar, embodied intelligence. How do you actually teach an AI to fundamental laws of physics? This slide shows the difference perfectly. Most of today's 3D models are kind of like hollow chocolate bunnies. They look solid on the outside, but there's nothing really there. Objects can just pass right through each other because the AI has no concept of solid. The new physics-informed models, though, they give these objects properties, mass, density, velocity, so they interact with each other and the world according to the laws of physics. So when we put all these pieces together, the end of the scaling era, this new focus on reliability, and these 4 new research paths, what does the future of AI engineering actually look like? This table lays out the new roadmap perfectly. The focus is shifting away from building just one giant, all-knowing model. Instead, it's about tackling specific, really difficult engineering challenges across different fields. How do you get rid of lag in robotics? How do you filter out all the noise online to find that textbook quality data? These are the problems that the top labs are absolutely obsessed with now. And this quote really says it all, doesn't it? We're leaving the wild west of AI, that phase where the goal was just to build the biggest, most powerful thing possible and just see what happened. We are now entering an era of disciplined engineering, where the focus is on building systems that are reliable, efficient, and actually grounded in reality. And this right here is why this whole shift is so important. The ultimate goal isn't just to build powerful AI. It's to build trusted AI. We need systems that we can actually rely on for high-stakes work, whether that's discovering new medicines, optimizing global supply chains, or assisting doctors in a surgery. And for that, capability just isn't enough. We need consistency. Which really brings us to a final, provocative thought. For years, the big question in AI has always been, what can it do? We were obsessed with its peak performance. But the question for this new era is totally different. What will it do, consistently and reliably, every single time? It seems like the next frontier of artificial intelligence might not be a test of its power, but a test of its character.